Was sponsored by Caseta by Lutron.
Imagine you have a giant circuit consisting of a battery, a switch, a light bulb, and two wires which are each 300,000 kilometers long. That is the distance light travels in 1 second. So they would reach out halfway to the moon and then come back to be connected to the light bulb, which is 1 meter away. Now the question is, after I close this switch, how long would it take for the bulb to light up? Is it half a second, 1 second, 2 seconds, 1/c seconds, or none of the above? Now you have to make some simplifying assumptions about this circuit, like the wires have to have no resistance, otherwise this wouldn't work, and the light bulb has to turn on immediately when current passes through it. But I want you to commit to an answer and put it down in the comments so you can't say, oh yeah, I knew that was the answer when I tell you the answer later on. This question actually relates to how electrical energy gets from a power plant to your home. Unlike a battery, the electricity in the grid comes in the form of alternating current, or AC, which means electrons in the power lines are just wiggling back and forth. They never actually go anywhere. So if the charges don't come from the power plant to your home, how does the electrical energy actually reach you? When I used to teach this subject, I would say that power lines are like this flexible plastic tubing, and the electrons inside are like this chain. So what a power station does is it pushes and pulls the electrons back and forth 60 times a second. Now at your house, you can plug in a device like a toaster, which essentially means allowing the electrons to run through it. So when the power station pushes and pulls the electrons, well, they encounter resistance in the toaster element, and they dissipate their energy as heat, and so you can toast your bread. Now this is a great story. I think it's easy to visualize, and I think my students understood it. The only problem is, it's wrong. For one thing, there is no continuous conducting wire that runs all the way from a power station to your house. No, there are physical gaps, there are breaks in the line, like in transformers, where one coil of wire is wrapped on one side, a different coil of wire is wrapped on the other side, so electrons cannot possibly flow from one to the other. Plus, if it's the electrons that are carrying the energy from the power station to your device, then when those same electrons flow back to the power station, why are they not also carrying energy back from your house to the power station? If the flow of current is two ways, then why does energy only flow in one direction? These are the lies you were taught about electricity. That electrons themselves have potential energy, that they are pushed or pulled through a continuous conducting loop, and that they dissipate their energy in the device. My claim in this video is that all of that is false. So how does it actually work? In the 1860s and 70s, there was a huge breakthrough in our understanding of the universe when Scottish physicist James Clerk Maxwell realized that light is made up of oscillating electric and magnetic fields. The fields are oscillating perpendicular to each other, and they are in phase, meaning when one is at its maximum, so is the other wave. Now he works out the equations that govern the behavior of electric and magnetic fields, and hence these waves. Those are now called Maxwell's equations. But in 1883, one of Maxwell's former students, John Henry Poynting, is thinking about conservation of energy. Now, if energy is conserved locally in every tiny bit of space, well, then you should be able to trace the path that energy flows from one place to another. So think about the energy that comes to us from the sun. During those 8 minutes when the light is traveling, the energy is stored and being transmitted in the electric and magnetic fields of the light. Now, Poynting works out an equation to describe energy flux. That is, how much electromagnetic energy is passing through an area per second. This is known as the Poynting vector, and it's given the symbol S. And the formula is really pretty simple. It's just a constant, 1 over mu naught, which is the permeability of free space, times E cross B. Now, E cross B is the cross product of the electric and magnetic fields. Now, the cross product is just a particular way of multiplying two vectors together, where you multiply their perpendicular magnitudes, and to find the direction, you put your fingers in the direction of the first vector, which in this case is the electric field, and curl them in the direction of the second vector, the magnetic field, and then your thumb points in the direction of the resulting vector, the energy flux. So what this shows us about light is that the energy is flowing perpendicular to both the electric and the magnetic fields. And it's in the same direction as the light is traveling. So this makes a lot of sense. Light carries energy from its source out to its destination. But the kicker is this. Poynting's equation doesn't just work for light. It works anytime there are electric and magnetic fields coinciding. Anytime you have electric and magnetic fields together, there is a flow of energy, and you can calculate it using Poynting's vector.
To illustrate this, let's consider a simple circuit with a battery and a light bulb. The battery by itself has an electric field, but since no charges are moving, there is no magnetic field, so the battery doesn't lose energy. When the battery is connected into the circuit, its electric field extends through the circuit at the speed of light. This electric field pushes electrons around so they accumulate on some of the surfaces of the conductors, making them negatively charged, and are depleted elsewhere, leaving their surfaces positively charged. These surface charges create a small electric field inside the wires, causing electrons to drift preferentially in one direction. Note that this drift velocity is extremely slow, around 1/10 of a millimeter per second. But this is current. Well, conventional current is defined to flow opposite the motion of electrons, but this is what's making it happen. The charge on the surfaces of the conductors also creates an electric field outside the wires, and the current inside the wires creates a magnetic field outside the wires. So now there is a combination of electric and magnetic fields in the space around this circuit. So according to Poynting's theory, energy should be flowing. And we can work out the direction of this energy flow using the right-hand rule. Around the battery, for example, the electric field is down and the magnetic field is into the screen. So you find the energy flux is to the right, away from the battery. In fact, all around the battery, you'll find the energy is radially outwards. Energy is going out through the sides of the battery into the fields. Along the wires, again, you can use the right-hand rule to find the energy is flowing to the right. This is true for the fields along the top wire and the bottom wire. But at the filament, the Poynting vector is directed in toward the light bulb. So the light bulb is getting energy from the field. If you do the cross product, you find the energy is coming in from all around the bulb. It takes many paths from the battery to the bulb, but in all cases, the energy is transmitted by the electric and magnetic fields.
People seem to think that you're pumping electrons and that you're like buying electrons or something, which is just so wrong. For most people, and I think to this day, it's quite counterintuitive to think that the energy is flowing through the space around the conductor. But the energy which is traveling through the field, is going quite fast.
So there are a few things to notice here. Even though the electrons go two ways, away from the battery and towards it, by using the Poynting vector, you find that the energy flux only goes one way, from the battery to the bulb. This also shows it's the fields and not the electrons that carry the energy.
I mean, how far do the electrons go in this little thing you're talking about? They barely move. They probably don't move at all.
Now, what happens if in place of a battery we use an alternating current source? Well, then the direction of current reverses every half cycle. But this means that both the electric and magnetic fields flip at the same time. So,
Hey, now that you understand how electrical energy actually flows, you can think about that every time you flick on a light switch. And if you want to take your switches to the next level, the sponsor of this video, Caseta by Lutron, provides premium smart lighting control, including switches, remotes, and plug-in smart dimmers. And since one switch can control many regular bulbs, you can effectively make all those bulbs smart just by replacing the switch. Then you can turn your lights on and off using your phone. Or you can use another device like Alexa or Google Assistant. Caseta works with more leading smart home brands than any other smart lighting control system. One of the things I like is setting timers. The lights in my office, for example, turn on by themselves every evening. And this feature gives you peace of mind that everyone in your household will always come home to a well-lit house. And once you're already in bed, you can check which lights you forgot to turn off and do that from your phone. Installation is easy. Make sure you turn off power to the switch first, and then disconnect the existing wires and connect Caseta's smart switch. If you need any help, they're just a click or a call away. Learn more about Caseta at Lutron's website, lutron.com/Veritasium. I will put that link down in the description. So I want to thank Lutron Electronics for sponsoring this video, and I want to thank you for watching.
Time. So at any instant, the pointing vector still points in the same direction, from the source to the bulb. So the exact same analysis we used for DC still works for AC. And this explains how energy is able to flow from power plants to homes in power lines. Inside the wires, electrons just oscillate back and forth. Their motion is greatly exaggerated here, but they do not carry the energy. Outside the wires, oscillating electric and magnetic fields travel from the power station to your home. You can use the pointing vector to check that the energy flux is going in one direction. You might think this is just an academic discussion, that you could see the energy as transmitted either by fields or by the current in the wire. But that is not the case. And people learned this the hard way when they started laying undersea telegraph cables. The first transatlantic cable was laid in 1858.
It only worked for about a month. It never worked properly.
There are all kinds of distortions when they tried to send.
Enormous amounts of distortion. But they could work it at a few words per minute.
What they found was sending signals over such a long distance under the sea, the pulses became distorted and lengthened. It was hard to differentiate dots from dashes. To account for the failure, there was a debate among scientists. William Thomson, the future Lord Kelvin, thought electrical signals moved through submarine cables like water flowing through a rubber tube. But others, like Heaviside and Fitzgerald, argued it was the fields around the wires that carried the energy and information. And ultimately, this view proved correct. To insulate and protect the submarine cable, the central copper conductor had been coated in an insulator and then encased in an iron sheath. The iron was only meant to strengthen the cable, but as a good conductor, it interfered with the propagation of electromagnetic fields because it increased the capacitance of the line. This is why today most power lines are suspended high up. Even the damp earth acts as a conductor, so you want a large insulating gap of air to separate the wires from the ground.
So what is the answer to our giant circuit light bulb question? Well, after I close the switch, the light bulb will turn on almost instantaneously in roughly 1/c seconds. So the correct answer is D. And I think a lot of people imagine that the electric field needs to travel from the battery all the way down the wire, which is a light second long, so it should take a second for the bulb to light up. But what we've learned in this video is it's not really what's happening in the wires that matters. It's what happens around the wires. And the electric and magnetic fields can propagate out through space to this light bulb, which is only 1 meter away, in a few nanoseconds. And so that is the limiting factor for the light bulb turning on. Now, the bulb won't receive the entire voltage of the battery immediately. It'll be some fraction, which depends on the impedance of these lines and the impedance of the bulb. Now, I asked several experts about this question and got kind of different answers, but we all agreed on these main points. So I'm going to put their analysis in the description in case you want to learn more about this particular setup.
If I get called out on it and people don't think it's real, we can definitely invest the resources and string up some lines and make our own power lines in the desert.
I think you're going to get called out on it.
I agree. I think you're going to get called out. So, I think that's right.
I think it's just kind of wild that this is one of those things that we use every day that almost nobody thinks about or knows the right answer to. These traveling electromagnetic waves around power lines are really what's delivering your power.